All right. Welcome back. Today is September the 23rd, and we're going to continue here on um, the practice homework for chapter 5. All right. So, um, we were doing DUs, calculating the degrees of unsaturation of different molecular formulas. And I didn't notice, but there was one left. So, we're going to tackle that one. So, we have that the molecular formula is C20H32Cln, and so we say that degrees of unsaturation is equal to 2 times the number of moles, which is 20. We're going to add 3 because we have a nitrogen, and we're going to subtract the number of X. So X is equals to 33 here because we have 32 hydrogens and 1 chlorine. So that's 33. Divide all that by 2, and let's see what we have. So we have 2 times 20 is 40, plus 3 is 43. 43 minus 33 is 10. 10 divided by 2 is 5. All right, so that will be that.
Hey, Dr. Odin.
Yes.
Would it not be... Oh, I was looking at the wrong one. Sorry.
Oh no, that's okay. No, I could be wrong. I'm usually sometimes wrong. Yeah.
Nope, you're fine. I was completely on a different... Okay, never mind.
Yeah, that happens. That happens. The vision, the eyes, play tricks on us. So, problem 3 here is a real life application of the importance of knowing the DU so that you can, calculate other things in the formula, or the in this case actually the structural formula. It says diazepam, marketed as an anti-anxiety medication under the name Valium. I think most of you have heard of this drug. Has 3 rings, A double bonds, and the formula C16. The H's we don't know, Cl, N2, and O. How many hydrogens does diazepam have? So the hint is calculate the answer without counting the hydrogens in the structure. All right, we can do that as a check. So this is like a math problem, honestly, applied to chemistry. So du, in this case we have 2 nitrogens, so that's important. We know that the general formula will be 2n plus what? What number do I put here?
4, because there's 2 nitrogen.
Exactly, 4. The first one adds to 3, and the second one adds to 4. If you had another one, then it would be 5, and you have 4, then it would be 6, and then like that. Minus x, and notice that I'm going to subtract 1. Why I'm subtracting 1?
Because of the chlorine?
Exactly, because of the chlorine. I'm not interested in total amount of X, I'm interested in total amount of hydrogens. So the X's include a chlorine, so we have to subtract that one. Divide all that by 2. And then the problem says that we have 3 rings and A double bonds. So that's a total of 11 degrees of unsaturation. And then we'll do 2 times n. N is 16 plus 4 minus x minus 1. Divide all that by 2. All right, so we're going to group these things. I'm going to take this 2 and put it on the other side of the equation. It's dividing, so it's going to be multiplying. 2 times 11. And here I'm going to start solving. 2 times 16 is 32. 32 plus 4 is 36. 36 minus 1 is 35. So 35 minus x. and I can now solve for x. In solving, I have the x is gonna be equal to. Notice that I can move the x to the left side of the equation, and it turns positive. 35 stays there, and 2 times 11 is 22. It's positive, so I take it to the right side of the equation, and it's now subtracting. So 35 minus 22, x is equals to 13. Therefore, there are 13 hydrogens.
How did you get? Where did the 11?
The 11? So the 11 are 3 rings plus 8 double bonds. That's equals to 11 degrees of unsaturation.
Okay, thank you.
You're welcome. And so my final formula will be it will be C16 H 13 Cl N2O. All right, let's count those hydrogens. I have 3 here, 2 here, that's 5. 5. Then 6, 7, 8, 9, 10, 11, 12, 13. So I have all my hydrogens. So I'm good there. This is diazepam.
Will it always be minus x minus 1 at the end?
Oh yeah, so we have an x that is chlorine. So I cannot just calculate this x by itself, because then that will give me hydrogens and chlorines. Because I have 1 chlorine, I have to subtract 1. If I had 2 chlorines, then I would subtract 2. You see that? From the x's. So I need to get rid of the chlorines in this question, because I know how many chlorines I have, so I have to subtract 1. That makes sense?
Yes.
All right. Okay, let's see what else we have here. Okay, so now we're done with the use. We're going to now learn how to read and analyze reaction coordinate diagrams. All right, check out this reaction coordinate here. It kind of reminds me like a little ghost. Ooh, you know, Casper. So we're going to analyze what's happening here. All right, we're going to answer these questions. Let's see how many questions. There are 4 questions. Question number 1. And you guys could participate, please. How many intermediates are formed in the reaction? And tell me which one are they. Anybody?
Are there 2?
2. Yes, there are 2 intermediates. Which ones are those, Kaylee?
I don't know. Like, do you put both letters together whenever you're talking about intermediates, or just the one?
Only one. So an intermediate is actually a product of that step. So what intermediates do you read?
Would it be C and E?
C and E. Very good. C and E. So this is the first step, and it makes C. So that's the first intermediate. The second step makes E. That's the second intermediate. So we have 2 intermediates, 1 product, 1 set of reactants, and then we have other things here. So let's see. Which letters represent transition states?
BDF.
BDF, very good. So B, D, and F, because they are on the top of the mountain. So that's the activation energy. BDF will be the answer for that. They represent the activation energy. What is the fastest step in the reaction?
Is
Would
it
it
B
be
because it's the shortest hill?
Yeah, the shortest hill, yes. What will be it?
B.
No.
F. Well, F, I guess.
F, yes. So notice that the distance from here to here is smaller than this distance, because you're comparing that to the free energy. This is the amount for B, and this would be the amount for F. So yes, F, not for F, I mean from EG. So this distance from here to here, this is what it would make this reaction be overcome, this transition state. So F is the transition state, but G is the product. But once this reaction gets to this point, she just falls down and finishes up. So notice that it's a step. A step is represented by the action of reactants to products. So we have that the answer for this is E to G. Is the fastest step in the reaction. This whole thing here is one step. All right. Which is more stable, A or G? And why? Anybody?
would it be G?
Yes. The answer is G, because it's lower in energy. So anything lower in energy, like here, when compared to this one, this is lower in energy. So G is the answer. It's more stable. Lower in energy means stable. High in energy means reactive. It's the opposite. All right, we're going to stick with that diagram, because I thought there were 4 questions. There's more for the same. Let's see. Okay, does A or E form faster from C? Which one forms faster, A or E?
A.
A, very good. So notice that starting from here, the activation energy to get to here, to this point, to make A, is shorter than going from here to D. Look at the distance in activation energy. So it'll take more energy. So A forms faster. A forms faster from C. Let me reduce this so we can see. What is the reactant of the rate determining step? Oh. What is the rate determining step first?
C to E.
C to E, very good. Is the tallest peak or the tallest bump. Now, what is the reactant of the rate determining step, if that's the rate determining step?
C.
C is the reactant. Yes. C is the reactant. I'm sorry?
Why is C the reactant?
Yeah, because now you're comparing this big peak here, big bump. And so this is reactant, this is product for this step. And this is your intermediate, D. So C is the reactant. If I would have asked what is the product of the rate determining step, then you have to say E. All right.
And you started at C because from C to E is the tallest bond.
Correct.
Okay.
Yeah. You see the tallest bump here from here to about here. That's the delta G, or activation energy, when compared to this one or this one. That's little. So this is your rate determining step. And so just by looking at that one lonely step right there, then you can say that C is your reactants, D is your product, and D is your intermediate for that reaction step. All right. All right, let's continue. Is the first step of the reaction exergonic or endergonic?
Endergonic.
Yes, it's endergonic. So now we're looking at this step only. Notice that C is higher than A. So here you have a positive delta G. All right, so this reaction step is endergonic, also known as endothermic. Now tell me this one. This one, you have to analyze this. It says, is the overall reaction exergonic or endergonic? What will be your answer?
Exergonic, because G is lower than A.
Exactly. Exergonic because G is lower than A. Excellent. All right. Which is the more stable intermediate?
C.
C. C has the lowest free energy, delta G. This one. Between those two intermediates, C is the one lowest. So C has the lowest free energy, also known as delta G. All right. Which step in the forward direction now has the largest rate constant? Wait, which step in the forward direction has the largest rate constant? So what is the largest rate constant? So if you have, remember when we say that when your rate constant is high, that means what? Faster or slow? That's in chapter 2. It's faster. When your K, or rate constant, is low, then is slow. All right. So when this number is high, like 10,000, versus 1, if you have a scale here of k, and this is 1, anything closer to 0 is slow. Anything higher than 1, let's say in the thousands, this would be fast. So a high K means a fast reaction. So which one is a fast reaction there? Which one is the fastest reaction?
E to G.
E to G, very good. So E to G has the smallest bump or hump to go over. Has the smallest activation energy therefore the fastest rate. So we're putting together all these concepts. Which steps in the reverse direction has the smallest rate constant now?
Is it A to C?
Oh, we're doing on the reverse direction.
Reverse.
Starting from G now. We're flipping the tortilla.
So would it be E to C?
E to C. That's a really good guess. That would have been my guess too, but the answer is G to E. Because now notice that G to E has the largest activation energy. So you go from here all the way up to here to reach. You see what I'm saying? So now we're going on the reverse. It takes a lot of energy to get to here and to form E. So G to E is the opposite. In the reverse reaction, this is a trick question, honestly. This is a really tricky question. Has the largest, but this kind of questions should challenge your brain to think. Has the largest activation energy therefore the slowest rate. And that makes sense. If this was the fastest going forward, if this step was the fastest reaction step going forward, it should be the slowest going backwards. How cool is that? Interesting, huh? That's how you have to think. All right, 8:50. My time is up. So we're gonna continue with 5 through 7 on Friday. We're good. We're on target. Have a wonderful day, guys. I'm gonna stop the recording now, and I'll answer your questions.